go. All right. Welcome, everybody, to my presentation, Beyond the Horizon, a security analysis of two VSAT systems. I've already received a small introduction. I'm a researcher for satellite and space system security. I've been here already last year talking about how to exploit a few satellites. I'm a PhD student at the Ruhr University in Bochum. I've been a visiting researcher at the Cyber Defense Campus in Switzerland. I'm the organizing and general chair of the SpaceSec workshop, so if you're interested in academic research on space and satellite system security, that is maybe the place to go. Just look up SpaceSec online. Okay. I'm also the subgroup chair of the integration layer of an upcoming IEEE standard. So if you're interested in integration layers, if you want to contribute to an upcoming IEEE standard, if you just want to see how these kinds of processes work, please let me know. We are always looking for new volunteers and interested parties. I also participated in the HackerSat 2 and 4 finals. So the HackerSat 4 finals were last year in Vegas with an actual real satellite that the Space Force launched. So this year and today I'm going to talk about VSAT, uncovering inherent security issues in current VSAT system practices. There's an academic research paper that we published at CYSAT. It will be public soon. You can already find it on my website. And specifically, the idea in this paper is basically attacking VSAT user terminal. So it's definitely not a new idea, but we are looking at it from a perspective of how can you directly inject malicious traffic onto these systems. And this kind of came from the VSAT incident. So basically, this entire research project started right after this VSAT incident in Ukraine, after the Russians attacked the VSAT service to get a large-scale outage in Ukraine to, well, disrupt communications. But it also had some fallout in the rest of Europe. For example, the wind farm in Germany was, for example, not reachable for an extended period of time. And it was around that time that we kind of started this project and kind of wanted to look into what kind of security issues do you find in these systems. So obviously there was some documentation about how the VSAT incident worked, or there was a rough idea at the time. So basically it worked in a way that attackers basically came through the internet, they compromised some ground services, some VPN services, and from there basically distributed malicious data, malicious payload, and that's in that case a specific firmware update that basically broke these modems. And this leads to, well, you have broken modems, but more interestingly, for example, in the VSAT cases, what exactly did they send? How did they exploit this? And for this, we looked at two modems, and one of them is a VSAT modem that will be in the second part of the presentation, but we also looked at the modem series of one other company. And really, the entire architecture of such a VSAT system is that you have a local LAN network, and this local LAN network is connected to a local router. Basically the same as in your home setup. You have your Wi-Fi box that is connecting to the internet, but in this case, we are connecting to some satellite antenna, and the satellite antenna is basically communicating with a satellite. But the satellite is basically just a bent pipe, so it's really not doing much more than relaying the traffic that is coming from the actual ground station. And the ground station itself then has some internal services that, for example, relay the traffic to the internet. So in this figure here, everything that is blue is basically internet traffic, or if you want to be more on a space side, it's user plane traffic. So everything that the user transmitted can also be non-internet traffic, of course. And then the yellow part, the orange part is the more interesting part that we looked at. That is the control plane. So in satellite operations, you usually have different layers of control plane. One control plane, that is what I, for example, presented about last year, is about a control plane that you use to directly control a satellite. So if you send commands to a satellite, then this is the control plane of that satellite. For VSAT architectures, there are also two additional control planes, and one of them is basically separated via, for example, VPN. And the entire idea here is that the user plane, for example, the internet traffic, and the control plane, so for example, whatever is basically managing the remote devices, is coming via the same physical link. So it's both on the same radio frequency, it's oftentimes also in the same modulation. There are also ways to separate the control plane differently. It's not always the case, but for the ones that we looked at, this was the case. And then you have a network interface, which is then usually the actual modem box that is kind of separating these two traffic flows. The blue flow, again at the top, is going to the router and then to the local area network. So this is the internet connection. You also have features such as a PEP, so for example, a performance enhancing proxy. This is kind of there to make your internet connection less sluggish. So when you're communicating via these old VSAT systems, we're not talking about a new Starlink system, but these old geo-based systems, then you have a very long delay of half a second per round trip, basically. And this introduces issues for certain types of TCP communications. One, it becomes sluggish, and some tools also just straight up run into timeouts. So these PEPs are basically there to send already, okay, the TCP connection works fine. They're kind of a good man in the middle, so to say. And then the more interesting parts, the control plane, is separated into a few things. Mostly it does basically configuration of the modem, for example, beam tables, what kind of modulation, what kind of back channel, what are the different time divisions to actually talk to the satellite again. Obviously software updates, something that we specifically looked at, and also telemetry. So what kind of, for example, quality of service information can we get back from the user terminals back to our base. And then there is this interesting side channel that is kind of in this orange dotted line, where basically the separation is supposed to be, well, you can't penetrate it. That's supposed to be in separation. But in this case, you can, for example, access the web interface of these VSAT terminals, sometimes from the internet, and then you can basically access this web UI, which is meant for configuration, which is then more meant for the control plane. This is not what we are doing here. There are, for example, some Black Hat talks from many years ago that already found out that if you take a long list of IP addresses from VSAT modems and basically just try to reach each of them, then there's a good chance that there's a web UI behind them, and oftentimes these web UIs do have some vulnerabilities. But it's also pretty interesting that you can just reach the management interface of these remotely. And the attacker models are really, we have basically an attacker that is right next to the antenna. For example, they're flying with a drone right into the communication beam between the antenna and between the satellite to inject information or to eavesdrop information on the traffic stream. Or maybe somebody setting up a rogue VSAT terminal essentially, so they're also using the satellite. There are a lot of restrictions, so depending on the geometry of the satellite dish, etc., you can't just set anywhere on Earth up such a VSAT terminal. It doesn't work that way. But for us, it's more on a technical, logical side. You can set up this kind of terminal somewhere, and if you're basically using a higher amplitude in the communication, then you might also overshadow the signal from the original one and can basically relay traffic to a lot of different VSAT terminals. It's kind of the entire use case of VSAT in the first place. And then lastly, we have basically this scenario where we try to map the VSAT incident, where people basically came from the internet and compromised the services that are exposed to the internet, and from there went basically on. And to kind of learn how these different vulnerabilities might play out, we looked at two systems. The first one is from NewTek, now part of iDirect, the MDM2200, or also called the SAT3 Play protocol. So this is the kind of board that you can see here. We just have a pretty regular ARM processor. Then we have some FPGA that is doing some DVB-S decoding and error correction. We have a demodulator. We have a digital to analog chip, and obviously vice versa. A pretty standard board. And the first step was obviously to dump the firmware. So how do we get the firmware of these images? Since we didn't get it obviously from the supplier, in that case, again, web UI might be vulnerable. So in this case, we have the web UI is basically run by a list of bash scripts. So basically, when you visit the configuration page of your own VSAT, of your own VSAT modem, then there is a bash script in the background constructing the web page, and some of the inputs are not properly sanitized. So in this case, when you go to CGI bin endpoint and then add some default parameters, then you can also basically inject the string, which it just adds a netcut listening port. If you use that specific exploit, it won't quite work because you also need to change the firewall a little bit, but this wouldn't fit on the slide to also change IP table rules, and it's not interesting. So it doesn't work copy-paste. Anyway, the interesting part is that basically they're trying to configure multicast addresses, and in that context, they're taking this multicast address, MC, multicast IP address 0, and they're trying to basically evaluate this into a list of different IP addresses. But they're not properly sanitizing what kind of data there might be. So we can also inject basically evaluation statement in bash. And now we can get a remote access to the terminal and can dump the full code. And it was pretty useful since we then learned how exactly all of this works. So basically we have it runs a regular Linux system. And when I say regular, I mean a super old one. So not actually a regular one. We're talking about Linux 2.3, I think. This is as ancient as it gets. And And basically, they have a lot of different drivers for individual components. For example, the demodulator that I previously showed on the slide, the hardware component, has its own driver. And then they also create from all these drivers, for example, also for the FPGA, for the digital to analog converter, they create a virtual network device called modem. And now they just have in their Linux distribution a nice network device, which from where they can just use IP, TCP traffic. And this is also what all of their applications then use. So for example, one interesting application is the modem controller that is basically receiving commands via some format, also emitting some form of telemetry. It also does the authentication. Okay, this is actually a valid modem for a paying customer, so you may proceed. And then we have this interesting software updates service, which we'll come to in a second. But first, the modem controller part essentially does hub-to-terminal envelopes, which means you send from the VSAT hub, so the part that is connecting to the internet with the large antenna side. You send a message to the actual terminal, and they're just using Google's protobuf to do that, and basically send a message there. Now, this is basically the code that does the translating. It's a little bit too much code that somebody can already see the issue here. But what essentially they're doing, all of these values that you can see here, everything after this is basically attacker controlled. And what they're doing is they're checking, okay, is there an encryption flag? If not, then the message is already broken and we don't care about it. But if there is no encryption flag, or if there's an encryption flag, there's still an exemption. So if the counter, the packet counter of packets received is 0, then we are just taking the message. And otherwise, we are decrypting it and then assigning it. So if we set a counter to 0, we can already get around this, but this in itself might not be an issue since, well, maybe not every packet that has counter 0 is an actual vulnerability. Oh, sorry. So in the next part, what they basically do, so here they have their secure envelope decode. This is the function I just showed you. And then in the next part, what they're doing is they take the counter again and change it, check it against the counter that is internal in the modem. So the modem also keeps track of all the packets that come in, keeps the counter, and then compares that counter. And then they do encryption manager, receive counter match. If it doesn't match, receive counter match is false. And then that should be the end of the things. Unfortunately, it's not, because there's also this extra end. This secure envelope.counter is unequal 0. So if we set the counter to 0, we also negate this statement, which basically is supposed to fix if the counter is out of order. So whenever we send the packets with counter 0, we can always get around packet encryption. And probably what happened here is that they didn't mean to use the secure envelope.counter, but rather encryption manager counter. Small issue, but now we can send unencrypted packets. And even if we weren't able to send these packets, the encryption is ECB mode. The packets are rather large. They're rather predictable. So there's a good chance that we could do some replay, reorder, or forging of blocks. They do have some kind of replay protection, they call it, but this is, again, based on this counter, which is already broken in the format itself. Now, at least these configuration messages are in some way encrypted. That's at least an attempt, and they did a small issue, or they have a small bug vulnerability where they just would have to fix one piece of code, and then it's fine again. Unfortunately, there's a bigger problem, and that is the updates. The updates don't have any protection at all. So basically, the updates work in a way that there is a broadcasting protocol that basically continuously announces how many where you get a new version. So for example, you can get a new version for a specific hardware revision on a specific port, and then for example, just find your version on this multicast address and this port, and then you can listen to this and get your new update. First of all, these packets are non-encrypted, but it's just the announcement, not so much of an issue, right? For example, this is the format of the packet that I was just showing you. So this is from Wireshark, the packet that we captured. And this is kind of the first start of it. Basically, it's saying UImage and then octet. And this is really the only interesting part, because now they have a function that is doing the parsing. So they do parse info, and this entire block is basically the info. And they do this interesting scanf buff plus offset with an unlimited, string. And people should already be able to see the vulnerability here. Basically, you can send this octet string as long as you want. And if it's longer than 80 bytes, then we can overwrite the program counter, and we have a full buffer overflow. And from there, it's the exact same thing as my talk last year. They have no ASLR on the specific version. They have no stack canaries. They do have non-executable stack, but in this specific case, the ROP chain was one single element, which was pretty convenient. So we can send one single packet to get remote code execution on the system. That is pretty convenient. And we actually tested this end-to-end. So what we did, we bought a block-up converter, so basically something that takes an SDR signal and up-converts it to KU band. And then we tested this in a lab. So this is I think we call it Echo Freak chamber. It's not exactly my area of expertise. I'm more the software guy, and other people did the wireless part. But basically, we took the actual modem and its antenna, and then we took the actual signal, and then we just send it remotely to the antenna, and we're, well, getting a remote shell on the system. So this is pretty useful. All right, so the next part, not quite as technically deep, about the VSAT surfbeam modem. How did we get the software there? So first of all, we obviously tried, again, the web UI for some vulnerability. Unfortunately, it wasn't that easy, or I guess fortunately, because this way is actually way cooler. So basically, at the end of the board, there are UART access ports. So you can see this little cable here. This is exactly where you basically have the two UART pins. And when you connect them, then you can already get the boot messages. Nothing super interesting. That's what you get quite often. You just get a boot up message. Okay, we're testing some values. And after some time, it's basically just telling you, okay, turning off console early because it's not configured to be used that way. But by looking through this, it says software CRC check pass. Doesn't sound weird. That's completely normal to do. But what if it fails? So what did we do? We basically made it fail by basically grounding a chip on the pin on the flash chip, and now all of a sudden it doesn't work anymore, and we get a prompt. Oh, okay, now it's receiving commands over UART. That's pretty useful. And this way we could basically change the boot arguments, boot it again, and then all of a sudden you get a telnet access that is without password and with root access. That's super useful. So it's basically remote maintenance, or, well, on-site maintenance. Pretty useful just by a fault injection. We also did the same for the surfbeam Pro. There it's slightly different since the pins are a little bit trickier to get to. We also grounded the pin, but there you have to do it 3 times in the right timing, and then you also get an access and can dump the software. So we didn't quite find such fundamental vulnerabilities in the iDirect system. The iDirect system is using the DOCSIS Mac security layer, which already gives it on the Mac layer pretty decent security. We did, however, we're also looking for more something that could explain, for example, the VSAT incident, because at the time there was exactly 0 information about what exactly happened. So what we found was basically they were using a DHCP protocol, nothing out of the ordinary, but they were using a special extension to this called from RFC 2132. And this can be used to, for example, announce different services or additional services within the network. For example, they can write, okay, our CWMP server address, or also the ACS, is at specific IP address. Or they can say the FTP server address is at a specific address. Also, in itself, nothing too worrying. But the scenario here is that somebody, like in the VSAT incident, already compromised parts of the ground station services. Not to the degree that they could push software updates, because then it would be a trivial scenario, but rather they compromised, for example, something that doesn't strike somebody as a security critical service, such as a DHCP packet service, or such as, for example, telemetry monitoring service, quality assurance service, or quality of service management. All of these things would be probably in a different subnet, since they're not super security critical. So if an attacker advances to these, there might be a good chance that this is handled differently than when somebody compromises, for example, a full CWMP server. But in this case, we were able to send DHCP messages, and we were, for example, able to set the new CWMP server address. So CWMP is a protocol that is also called TR069, which is often used for remote maintenance of these assets. And basically, when you send a new DHCP packet, you can set it a new address, and the modem will immediately look up this new address. So you can host a service, or you can host this address in the internet. Basically, it then responds to the service. We tried that, and basically say, do an update. An interesting part here is they're not authenticating the new service. So whenever it's talking to a CWMP service or to this FTP service, they're never checking, is this actually a service I'm allowed to talk to, or is this does it have any certificate? There is no authentication from the server towards the client. And so anybody can host these services. And if we can also send one single DHCP packet, we can also make them use that specific service. And then we can also send the update. Interestingly, the update in itself is also encrypted, but you can bypass that encryption by basically sending a specific file. So if you send basically a file, it's not quite that file name, but no encryption. If that is on the right place on the file system, then you can basically disable the encryption, and well, you can create this file using the specific service. So if you basically send one request to create this file and then a second request to pull an update that is unencrypted, you can break the entire modem. You can do a full modem software update just by sending a single DHCP protocol, which seems pretty off, and at the time, specifically interesting since people were reporting an increased traffic of DHCP protocol during the VSAT incidents. Now there's a lot more information, so this is more or less outdated, but it still works that way, and I think that's pretty interesting. All right, any questions?